Just a minute. Okay, so we are good to go. It's live on YouTube now.
Yes, sir. Good morning to all. I welcome all the participants and speakers of this FDP program and the other participants also. Today we have Dr. Daniel Raymer with us, and he is going to deliver a talk on conceptual design of winged hybrid airship and other LTA systems. I take the opportunity to introduce Dr. Daniel Raymer. Dr. Daniel Raymer is president of the design and consulting company called Conceptual Research Corporation and serves as program manager, configuration designer, and chief engineer for its varied projects. Currently, these include the DARPA flying missile rail and the Raymer manned Mars plane and a proprietary high altitude unmanned aerial vehicle. Recipient of the prestigious AIAA Aircraft Design Award, Dr. Raymer is a recognized expert in the areas of aerospace vehicle design and configuration layout, computer-aided design methodologies, and design education. During his 10 years in the Advanced Design Department of Rockwell, North American Aviation, he conceived and did the layout design for Rockwell's entries in what became the F-22, B-2, and T-45 programs, and was head of air vehicle design for experimental vehicle X-31 from blank sheet of paper CAD screen to the configuration that flew with minor fabrication-driven changes. His industry career includes positions as Director, Advanced Design with Lockheed Martin, Director, Future Mission at the Aerojet Propulsion Research Institute, and Project Manager for Engineering at Rockwell North American Aviation. He also served as a research engineer and aerospace design consultant at famous RA&D Corporation think tank. Dr. Raymer is the author of best-selling textbook, Aircraft Design, A Conceptual Approach, and the well-recorded layman's book, Dan Raymer's Simplified Aircraft Design for Home Builders. His biographical book, Living in the Future, The Education and Adventures of an Advanced Aircraft Designer, covers his career and design projects, including most of those described below. With this introduction, I request Dr. Daniel Raymer to take over the session.
Yes, hello everybody. It's nice to give this talk. It's different from the talks I usually give, and I normally teach short courses on aircraft design, but winged airships and LTA systems is a kind of different corner of that universe, and it's going to be fun, I think. I haven't given this particular talk before. I just put it together for this this particular effort going on in India. So I'm not exactly sure how long it's going to take. I hope I follow the proper schedule and don't overrun or underrun, but we'll just have to press on and see what happens. Before we get started, and let's see, before we get started, as far as the copyright of this, please let me advise everybody that you're welcome to view this, and they're welcome to put it on YouTube and on a website. But I'm not giving permission. I don't want people to take screen grabs of my slides and use them as your slides. Please know that this is all copyrighted material. Anyway, that's just a small heads up as we begin. So you just heard a biography of myself, so I won't repeat it all. But what I really consider myself is rather than all this stuff and rather than an author, I really consider myself an aircraft designer. I've been doing this really since I was a kid, but my very first job was at the old North American Aviation Company, where I learned how to do this from some of the history's best aircraft designers. My first boss literally designed the X-15, and my main mentor was the guy who designed the B-1 and the HIMAT fighter technology demonstrator. And the guys in the group did the F-100 and the F-107 and just all kinds of amazing aircraft. So I was very lucky to go straight into advanced aircraft design. And I was also lucky enough that I got to do lots and lots of blank sheet of paper designs. I don't think there's too many people in the world that got to do more blank sheet of paper designs at a credible company where somebody was paying you for it and where other people reviewed it and it went to the wind tunnel and all that kind of stuff. So I've been very lucky in that. Like as often happens, you design a lot of them and very few get built. In my own case, The one that I did lead the design of that got built and flown was the X-31, which is shown in the middle left here, the white and blue fighter thing. And to the bottom right, I did a lot of consulting on the design for Kratos, the BQM 167, 177. And I actually did the configuration design for their BQM 170, or sorry, MQM 178. I was looking to do that. And another thing that I did that was built, and it's what we're going to talk about today, is that thing shown in the middle right, which looks like a big blimp, and it's actually a hybrid airship. And I'll talk about that a little bit today. So anyway, these are some of the designs, and I'm also lucky enough that I get to continue doing it after all these years. I am still the lead configuration designer in the projects that I run. Right now, I'm literally writing a final report for a DARPA contract. And when I mean literally, I mean that's what I was doing 10 minutes ago. I was working on the final report. And it is a vehicle that I designed, and we took it into the wind tunnel, and we did a fabrication demonstration of the fuselage. It's fun. I love doing this stuff. I love my job, and I'm always happy to talk about this kind of stuff. So that's who I really am. I do write books, and I'll caution you that I'm going to assume you've got some working familiarity with aerospace engineering and aircraft design, the kinds of things that are in my textbook at the top left. And I assume you're all professors. I think you're all in aeronautical engineering or something close. And these are some of the other things that I've written. He mentioned the Living in the Future, bottom left. It's kind of a memoirs book. Next to that is the Simplified Aircraft Design for Home Builders. It's kind of an easy introduction. It's aimed at a fairly smart person who is not an engineer, kind of an average person who likes airplanes, but is interested in learning more. And on the right is the manuals and the software that I wrote. I did develop this RDS software, which is sold in a student version and also a professional version. I'm working on the book in the middle, the Engineer's Field Guide to Management and Business. I'm afraid I'm going rather slowly on it just because I have too many other things to do. But when I have a little bit of time, I work on it some more. I don't know when I'm going to be done, but I'm having fun doing that. Okay, I also teach a lot of short courses, including I've taught in India 3 or 4 times, and eager to go back, happy to. I'm not afraid of COVID, but everybody else is. So anyway, and I do keep a website, aircraftdesign.com. It's all free, and there's quite a bit of stuff there that is of interest to the aircraft design and aeronautical engineering community. So feel free to poke around. A lot of my papers are there for free. My PhD thesis, which is in aircraft optimization, is there, and it's all free. Okay, well, let me just jump into it. I wasn't sure what background people taking your program, what background you all had. So I wanted to start out with some of the fundamental equations and design considerations. And I know you've been through this in this class of yours already. So forgive me if I repeat myself a little bit, but some of the people that will look at this later, some of the people watching now don't have that background. And I do want to present that. I'll try not to bore you by doing it too slow, but let me run through some of the basics before we move on and talk about why hybrid airships are different. So that's the second item. And then the third and fourth are 2 hybrid airship projects that I've been involved with. One, the Ohio Airship Dynalifter, and the Egan Airship Plimp. And I know for sure that James Egan is watching this. Hi, James. And he's kindly given me permission to show some of this stuff. It's still an active project, so we had to be careful, and I had to make sure I wasn't showing anything that he's still keeping as a proprietary secret. I've also invited Robert Rist of Ohio Airship, and the Dynalifter project is rather old now, and it's not really actively being pursued, so he was fine with me showing anything I wanted to. And I think Robert is also on, although I'm not certain that he's on. If so, yeah, hi, Bob. I hope you're listening. Otherwise, you can listen later. So we'll go through that, and then I'll have some summary thoughts and some suggestions. I'm kind of proud of that picture there. That is me. And yes, I am flying the Goodyear blimp. I got about 20 minutes of time flying that right over Los Angeles. In fact, I flew it just about over my own house where I'm sitting right now. In fact, straight ahead, I think might be my house, or a little bit to the right, very near the Los Angeles airport. And that was quite an interesting experience flying that thing. And it does fly differently than a normal airplane, but you get used to it. And I thoroughly enjoyed that. Okay, so let's move on. let's talk about some of these things, some of the background physics. I think you all know this. It all fundamentally starts with Archimedes. And of course, you know, the story is he was sitting in the bath and noticed the water running out. And somehow it occurred to him that, that there must be a lift force on his body equal to the weight of the water that ran out because he sat in the tub. And that's a pretty smart thing to think 3,000 years ago, long before Isaac Newton. And, you know, for every action is an equal and opposite reaction. So somehow he got that idea. And that's kind of the basic of all of this stuff. So the buoyancy you get is determined by the weight of the displaced fluid, which in our case is air. So we put a shape up there that displaces air, and you can calculate from the volume how much air is displaced. And now all you have to do is figure out the density. Okay, well, we have tables, we have data on the density of air. There's the usual values, standard day air in British imperial and also in metric units. Yeah, it's just that easy. So that's how you calculate the total lift that you would get from displacing the air, but you have to displace it with something, which makes it a little more complicated. But then the air density itself isn't a constant, so you have to know what the air density is. And it's affected by lots of stuff, of course, altitude, temperature, pressure, and also humidity. So to find out what lift you get from a displaced amount of air, you need to find out that. We use Charles' laws and Boyle's law. Those were invented a long time ago. Who knew then that it would be used for flying? But they are. So the effect of temperature is if pressure is held constant, and that tells you the density variation. And Boyle's law is the same thing, except here it's the effect of pressure if temperature is constant. And of course, you just combine them and get a single law that I don't think anybody named, but it's just a combination of those two. So then you have to worry about the other effects. So those are the pressure and temperature. And then what about the moisture, the water vapor? And that's a problem because water vapor is less dense than the air it displaces. We get lift by displacing a weight of air. And if the volume of air you displace is less dense, you get less lift. So moisture is bad when it comes to airship lift. Depends on temperature. So if the air is really cold, it doesn't hold very much moisture. Those of us that have lived in very cold climates know that. When it's really, really cold, the air is also really, really dry. A lot of us have problems with our noses. They all dry out inside when it's really cold outside. So anyway, you have to decide as you're designing your airship what saturation, what percent of humidity, and 50% is nominal use. So, you know, like I said, we're working our way through these fundamental equations, and I hope you're all familiar with this, and I'm boring you to death, but at the very least, you can look at my funny cartoons. So, okay, so that's the density, or that's the mass of air that we displace. It's purely based on volume, but unfortunately, we typically have to fill that up with something else. But if you could do it, the really best thing to do would be displace the air and not put anything in it, not put anything in that volume. So the best thing you could do would be to have a hard vacuum. If you could somehow make a shell that would weigh almost nothing and would literally hold a complete vacuum, that would be the very best hydrostatic lift. Of course, we don't know how to do that. A lot of research on that and thinking about it, but nobody really knows how to do that. If you made something that looks like a balloon that literally had a vacuum inside, it would be extremely dangerous. A tiny pinprick and the whole thing would implode and then explode, and not good. So anyway, the best would be a hard vacuum, but we can't do that. So instead we put something else where we wish to displace the air. And what we do is we put a gas there. So we have these things, we call them lifting gases. They really don't lift. In fact, it's the opposite. Lifting gases actually push down. But the trick is, of course, they push down less than the weight of the air that they displace. So that's the whole trick here. So anyway, so the net lifting force then is the lift that you would get if you completely displace the air. It's the weight of the displaced air minus the weight of whatever you put in there. And there's three things we put in there normally. There's other possibilities, but normally the three lifting gases are hydrogen, helium, and just hot air. Hydrogen is, of course, the best, about 68 pounds per 1,000 cubic feet, or 1.1 kilogram per 1,000 liters. Very common element, greatest lifting capacity, wonderful. You can produce it a couple of ways: electrolysis, chemical reaction. In our American Civil War, the balloonists would travel around with big vats of acid and you throw metal in there and hydrogen bubbles off. So that's how they did it. You can also use electrolysis. We have that technology now, although the equipment is not lightweight. So it's very good. The only problem, is, of course, is it explodes, or at least it burns very vigorously. So it's forbidden in passenger carrying airships. There are people who are revisiting that and saying maybe it's safe, or at least safe enough if we're careful. And they also point to the famous disasters like the Hindenburg. And they say, well, it wasn't really that the hydrogen exploded. It was more the fabrics covering the fuselage. And they had this old dope paint that burns so well. So it's still being debated. But if you want to use hydrogen in a passenger carrying airship, you have to convince a lot of people. We normally use helium, a little bit less lift, 68. Instead of 68, you get about 60 pounds per 1,000 cubic feet. That's not too bad. That's a little bit of a loss. If you take that ratio, it only means you have to make your hull a little bit bigger if you photo scale it in all dimensions. I forget off the top of my head. I think it's 15% bigger or something like that. That's not too bad. It'd be the cube root of 60 divided by 68, or the inverse of that. Anyway, so yeah, you get about 10% less capacity for a given volume. It's completely safe, but the problem is it's inert. It's so safe that it doesn't actually form compounds of anything. Since it doesn't form compounds, you can't look for it. You can't dig it out of the ground and convert it from something. Instead, you have to find it as helium. And you sure don't find it in the atmosphere because it all goes up. So you have to, luckily, it is actually blended in natural gas deep under the ground. It's still down there. And so if you take up natural gas, you can, in fact, sort it out from natural gas. And that's where we did it. It's expensive. It's not available everywhere. So there's always sort of practical aspects. And also because it is expensive and not available everywhere, you really don't want to throw it away. So we try to design the airship so we don't throw it away. The final one, of course, is hot air. Just heat it up with a burner up to a pretty hot temperature there, hot enough to kill you instantly. And you still don't get very much lift, not even a third of what you get from helium or hydrogen. All right, so those are the basic options for a lifting gas. That picture there, if you're not familiar, Alberto Santos Dumont, who was from Brazil and moved to Paris. He made a little tiny hydrogen balloon, which you see here, very tiny, 4,100 cubic feet, incredibly tiny, probably the smallest man-carrying balloon ever made. And the whole thing, including his gondola and everything, except the hydrogen, the whole thing weighed 50 pounds. He would literally put it in a suitcase and haul it around. And then all he had to do was get somebody to pump it up full of hydrogen, and off he would go. Okay, now another thing about the gas that you do have to take into account is its purity. Whatever you put in there, which is probably hydrogen, it's going to leak a little bit. It will leak out and air will leak in. And so you have to avoid that as much as possible, but then you also have to take that into account in your lift calculations. If you get the slightest bit of leakage, you don't want to immediately ground your airship. So you have to make some assumption as to how much impurity you will allow. And then if it goes below that level, you have to either replace the gas or scrub it. You have to run it through some kind of a process that pulls out air and gives you just pure helium. There's typical numbers. The 1930s, about 2 to 3% a year loss of purity. Today, better than that, probably 1 to 1.5%, but you probably can't do much better than that. So you do have to take this into account, and you have to assume a worst case level of purity and put that in the calculations. All right, altitude and temperature effects. When you go up in altitude or when the temperature changes, the density of the air changes, but if it's not physically constrained, if it can expand, then the density of the gas, the lifting gas, also changes, with the odd result that the total lift is not changed. So that's a nice thing. So this is a Explorer. This is a 1930s research vehicle. It was a big balloon, hydrogen, if I remember correctly. Yeah, hydrogen. Not sure. I think it was hydrogen. In any case, a very big balloon that they took up. It was a manned balloon. It went up to 72,000 feet. That was by far a world record. The regular airplanes at that time, most of them were still biplanes. So this was very high, all kind of records. And it was launched this way, hanging down like this with a whole bunch of extra volume. But up at high altitude, that gas expands to roughly this shape. I looked for a photograph of it already expanded, and then I realized who would have taken the picture. There was nobody else who could get up that high to take a picture of it. So I had to guess. So this is about what it looked like fully expanded. Anyway, so that's what happens with the gas. And this is always a design problem. You basically design it to be completely full at some chosen altitude, which we call pressure height. So it's fully expanded at that altitude. If you go higher, if you don't have any way to either vent off the gas, or if there isn't any flexibility or something, you're going to pop the bag. So it's very important to know that. And then the inverse calculation is necessary. And that is, you decide what altitude you want to be able to go to. You pick a pressure height, and then you have to calculate how much extra volume you need to fly at sea level. And you have to somehow take that into account. So percent fullness, easy calculation. It's basically the ratio of densities. Or you can ratio it by pressure and temperature using Charles and Boyle's law. But the percent fullness then tells you the fullness at sea level to give you a required pressure height. And if you just invert that, that tells you how much to oversize the bag volume. So you have to do that though. And then you have to take into account the fact that when you're down low, you don't have as much lifting gas. The volume of lifting gas is far less than the total volume required to take into account the percent fullness calculation. So you have to do something, and the usual thing we do is ballonets. They're little balloons within the balloon. You all know that by now. Basically, as you go up, the lifting gas expands and pushes the air out of the ballonets. When you go back down, you have to get air back into the ballonets, and that can be a problem. There are alternatives. You can have super pressure balloons. You can have a balloon or gas bags in a dirigible that are designed to go to a higher pressure. In other words, they don't pop when you go up too high. So you can do that, and that's certainly something that people do, and can consider that. And that way you don't have to oversize the balloon so much at low altitudes. The other thing you can try to do is you can try to compress the gas. So as you go up in altitude and it tries to expand, just compress it, put it into some kind of tanks. Probably not a good idea to have a whole bunch of heavy metal tanks, but people are looking at basically what looks like rubber bags, or even sort of donut shapes, like car inner tubes that are all wound with Kevlar and stuff like that. And I'm not sure what the current state of the art is, but basically something lightweight and flexible that can nevertheless take the high pressure. And then you have a pump, and you take the lifting gas and you pump it into these things. So those are the different approaches. So let's talk a little bit about airship design considerations. First of all, the ballonets. Down at the bottom, you can see actual ballonets. This is a patent drawing for one of the early Navy blimps. And you can see they're pretty large. You do the percent fullness calculation, and that tells you how much volume you need in the ballonet, basically, as well as telling you how much to oversize the whole envelope. To the right, you see Alberto Santos Dumont. He was actually the first guy to come up with a really successful airship. He did it before Zeppelin did it. He was actually able to solve all the problems of airships around 1898, 1899, and flew an airship with a internal combustion engine. He figured out the problems with steering. He figured out pitch control. Other people had invented the ballonet, but he sort of perfected it and got it to be practical. And he actually wound up with a very practical flying machine, and he was just flying everywhere. This is 1901, and he won a prize by flying around the Eiffel Tower and following a certain course. Very interesting history, Alberto Santos Dumont, and it was fantastic. He had a real working, no kidding flying machine. He would actually fly, not this one, but a slightly later version. He would fly it to restaurants and land it on the roof, tie it up, go down, eat his food, go back up, untie, and fly home. And this was before the Wright brothers flew. So he had it all worked out. Okay, so anyway, on airship designs, looking up at the top here. So a couple of things. One of them is if you're used to airplanes, with an airplane, we always have a reference area, and it's the wing, and it's this sort of trapezoidal reference area. It's sort of a top view cookie cutter look at a simplified wing shape, just a trapezoid shape that approximates the real wing. And we use that for aerodynamic references. Well, there's no wing on this thing, so what do you use? Well, sometimes they use the whole frontal area, which gives units of drag divided by dynamic pressure. And you can find tables with the drag expressed that way. But what is more common in at least classical airship analysis is they take the actual whole volume and they raise it to the 2/3 power. And they do that just to get units of area because that's what you need to non-dimensionalize drag and lift. So it's kind of an odd dimension, but that is what they use. They also have a thing called standard displacement, and a whole lot of the statistics on airships is based on the standard displacement, and that is the weight of air displaced by the hull, which is the volume of air times the sea level standard day density. So it's the standard day density of the air displaced by the hull. So that's what they use. It's kind of an odd thing. A couple more things to know about airships. They're often unstable in yaw. And I saw that when I was flying the Goodyear blimp. You pointed at something and it just sort of decides to go a little bit to the left, and you step on a rudder pedal and you bring it back over and it decides to go to the right. You're just doing that the whole time. It's like a horse. I went horseback riding a few days ago and the horse did the same thing. You point him in one direction and he just decides to go another direction. With the airship, it happens quite slowly, so it's not a real big problem. Sitting there and every once in a while you look up and there it goes again. So you step on a rudder pedal and it goes back to the direction you were hoping to go. Now in pitch, the hull is unstable, but you have the low center of gravity because the mass is hanging below the hull. And that basically fixes the pitch stability. So it's not so difficult in pitch. All right, down at the very bottom is a very classic tail sizing equation. And you'll notice that it is based on the whole volume raised to the 2/3 power, just like I said, that's kind of standard in airships. All righty, when you're designing an airship, one of the important considerations is the fineness ratio of the hull. And this is kind of an odd thing. And I got interested actually when I first got involved in airship design, when I did that Ohio airship. I was trying to decide what the optimal hull fineness ratio would be. And I have a very big library. If you look behind me, that's not even a fifth of my total library. And I dug through my old books. I have lots of old engineering textbooks. I dug through the old books and found some old books on how to design airships. And I looked for their recommendation on fineness ratio. And they said the funniest thing. They said everybody knows that the ideal fineness ratio is somewhere around 3, but all the successful airships have a fineness ratio around 6. And then it just went on to another subject. And I thought, oh, wait a minute, explain that one. And of course, the author's been dead for 80 years, so I couldn't ask him. So I decided to figure it out myself. And I wrote a computer code using the drag methods in my textbook. And I parametrically varied the fineness ratio. And I got it all ready to run the calculation. And then I realized, well, wait a minute, there's 2 different ways of changing fineness ratio. And one way that you can change fineness ratio is if you keep the same total volume. In other words, when you stretch out the length of it, you cut down the cross section. But in other cases, you might not be able to cut down the cross section. And if you look at that little airplane sitting there, there's somebody sitting inside. And if you stretch out the length to get a higher fineness ratio, you can't cut down the cross section if you don't cut off their head. So that's another way of doing it. In that case, you would increase fineness ratio by keeping cross section the same and just lengthening it fore and aft. Okay, so there you don't keep constant volume. Instead, you keep constant cross section area. So I real quickly rewrote my little code and I plotted out the answers, and it looked like this the very first time. I didn't cheat at all. This is what came out. If you assume the constant frontal area, you get an optimal around 3. If you assume the constant volume, you get an optimal a little bit better than 6. Okay, so that kind of explains this strangeness. So in that old textbook, he was actually wrong. For an airship, it is better to be up around 6. Now down below is a little bit more guidance that also includes the structural effects. if you have a very long, non-rigid airship, a blimp of some sort, and you make it long and skinny, you might have trouble with it. It might fold up in the middle. In fact, Alberto Santos Dumont's first airship did fold up in the middle when he was coming down because the pumps for the ballonets couldn't pump fast enough. And he literally didn't get enough air in the ballonets, and the whole thing folded in the middle and it almost killed him. So you don't want that. So anyway, down below is some of the sort of historic guidance. These are sort of successful airships, around 6 for a rigid one, just like that old book said, but a little bit lower than that for non-rigid and semi-rigid. In other words, ones that are more like a blimp. Okay, well, I hope you're enjoying this. Airship analysis, when you do the calculations, the methods in my textbook are pretty good. It looks like it works. Realize that it's a very high Reynolds number. So just make sure you use that equation properly. And it looks like actually it's even a little bit better than that. So I found I get numbers that kind of track with old airship wind tunnel data if I do the classic airplane methods and then lower it by about 15% or so. CL alpha is about 0.6 relative to that 2/3 of volume. So, you know, that's useful if you want to add the lift of the hull to any other lift calculations. When you do the airship analysis, you can't use a Breguet equation because the Breguet equation is integrating a change in weight, and weight is the downforce. And if you do the airship right, you don't have a downforce. That's the whole idea. So you can't use a Breguet equation. Kind of like electric airplanes, you can't use a Breguet equation either. And if you have an electric airship, you really can't use a Breguet equation. So you got to do it another way. And basically, it's just engine runtime, how much gas you have, how much electricity you have, multiplied by the speed you fly at. When you do acceleration calculations, don't forget all that stuff inside the bag has mass and it has to be accelerated. The fact that it doesn't weigh anything doesn't matter. It does still have mass, so you have to accelerate it. And for big airships, you also have to accelerate the air that sticks to the outside. And we call that apparent mass. And it's not trivial. So when you talk about accelerating an airship to some flight speed, now you have to take that into account. And there are approximate methods that work for that. Okay, well, let's see. I just put a listing here of airship regulations and policies. These are US regulations that need to be looked at. And so that's what I wanted to say in fundamental lighter than air equations. And I hope that was interesting and not too redundant for what you've already covered before, but I kind of wanted to start out with that. All right, well, let me move on now and talk about hybrid airships. And this is an interesting idea. It goes back a long ways. There's our friend Alberto Santos Dumont. That's him in the cockpit of a hybrid airship. What that really is it's the prototype of a heavier than air airplane that he developed after he basically invented the dirigible, or at least the successful dirigible, and became world famous. I mean, the guy was really famous. After he did that, then he wanted to move on and try to solve the problems of heavier than air flight, regular airplanes. And at that time, nobody knew that the Wright brothers were already flying successfully. So he thought he was the first to solve those problems also. And if you're interested in this story, it's a fascinating story. On my website, one of the papers that you can download for free is a paper I wrote in 2003, celebrating Santos Dumont, actually, and talking about what he did and then how he thought he invented the heavier than air airplane and eventually realized that the Wright brothers had beat him to it. So if you want, it's a light read. Anyway, okay, so there is Santos Dumont, and he's put a big gas bag trying to basically get into the air with a heavier than air airplane, but do it sort of safely. And if it didn't work out, not kill himself quite so quick. Okay, well, let's move on and talk about this. So why the interest in hybrid airships? I've actually had two different people hire me to do designs on hybrid airships, and they were both very enthusiastic about them. And there's reasons for that. And I put together a couple of charts talking about the potential advantages of a hybrid airship. And the very first one is a regular airship is difficult to handle on the ground. It takes a big crew. The bottom left photograph I took when I was getting ready to jump in the Goodyear blimp and fly it. That was a fun day. Look at all those guys there trying to hold it down, trying to move it around. When it comes into land, there's a whole bunch of long ropes that just hang out there all the time. You can see them when you're flying the thing. They just hang out in front, and a whole bunch of these guys will grab the rope and and try to catch that thing. It's like catching a whale. And if you notice, by the way, they don't hire little tiny guys for this job. Those are some pretty hefty guys because their own mass is necessary for making this work. So anyway, yeah, you have a big crew on the ground. And then after you've landed and you tie it up, you typically have to tie it to a mooring mast. You can't just tie it to the ground. So bottom right, you can see a mooring mast. This is an old airship, and this is real. Look what happened. It got caught either by a change in outside air density, which changed the lift, or maybe a big gust of wind, but something or other caused it to flip almost end over end. That's a big vehicle. And everything inside, of course, went to the nose. And anything in the back went to the front. Very dangerous for people inside. If anybody's inside, kind of hard to get out of that thing when all of a sudden you're kind of hanging from your straps. So not a good thing. And that's a serious problem. When these things are on the ground, though, you don't want to tie it down front and back to stop this from happening. Somebody's talking. Is that deliberate? Is there a question or?
No. I've muted them. They're about one careless participant. That's all.
I'm sorry. Was that a question for me, or shall I keep going?
No. Keep going. It was one of the careless participants. I've muted her. No problem.
Okay. I'm sure it was just an accident.
Sorry.
Okay. Well, anyway. Okay. So anyway, you can't just tie the tail to the ground, because then when the wind comes from the side, then you're really in trouble. So you have to have some kind of a scheme for handling this thing on the ground. It's just not an easy thing to do. Another problem is that after you've flown a while, you've burned off fuel. So it might be difficult to come down. And if you're on the ground or on the mast and you take the payload out, now the thing floats upwards. So you're always trying to balance it. And you can imagine, well, I'll just have water tanks and I'll fill them up. Every time I take 2 kilograms of payload out, I'll put in 2 kilograms of water. Well, that just gets to be awkward and unfortunate and difficult. And it seems like something that, well, it's a practical issue. And of course, there's solutions to it and people come up with solutions. But it is a big extra set of problems. One of the things that they do when you're cruising during flight, you burn off fuel. And so now you're light and you're too light to come down. So you either have to valve off some gas or possibly pump it and put it in a tank, which we really don't have that working right now. Or another thing that they do is they use the heat in the exhaust to basically condense water vapor out of the exhaust and catch it. So they actually catch water from the engine exhaust and put it in a tank. And this goes back a long ways. These are some guys holding condensers from the 1920s. The actual condensers are way bigger than this. This is just a sample. So anyway, that's another set of problems with the airship. It's the whole mass control thing. So it gets to be a problem. So anyway, the hybrid airship idea at least potentially offers a solution with this, because the idea is that it's sort of part airplane, part airship. And basically, it's not lighter than air. Everybody calls it LTA, but it's not. That's the whole idea. It's not lighter than air. It's heavier than air. And it needs the extra lift from wings or something else to get off the ground. On the far left is a cute picture that actually comes out of a children's book, a young boy's book aimed at people like 10 or 12 years old. And I grew up reading these books. I loved them, and I probably one of the things that pointed me towards aerospace. This was written in 1910, and it is an airplane with a big gas bag in the middle. And this one is really cool because back in 1910, fictionally, he could do something we still can't do today, which is suck all the helium out of that gas bag and turn it into just a pure airplane. And then when you want to land, you blow up the gas bag again, and then you become an airship. I don't think that's going to work. And if it did work, you don't want to crash into a building as he's doing. Anyway, I already mentioned Santos Dumont and reasons he tried that. And at the top left is this Ohio airship that I'll talk about a little bit later. Okay, so heavier than air. What are we trying to do here? All right, it's only partial hydrostatic lift. So on the ground, it sits on the ground. It sits like a normal airplane. It sits on a runway. You can set the brakes and walk away as long as the wind doesn't blow too much. Okay, so you get rid of all of that that issue, all of that problem, all of the big heavy guys trying to catch it, all the ropes hanging down, you get rid of the mooring mast, you get rid of all that stuff. It sits on the ground, it lands on a runway. Okay, wheels on a runway. In flight, you get hydrostatic lift, you get some of that airship benefit, and that reduces the need for aerodynamic lift. It's just a pure subtraction. So the drag due to lift is reduced, and you can get a very good lift to drag ratio. It's at lower speeds. If you go real fast, now you get a lot of parasitic drag from the big hull. And it's a big trade-off. I'll show you some charts later about what the trade-off looks like. So that's basically the idea. That's basically the benefit. Is it really better? I can't tell you that. I can tell you lots of design studies I did, and it looks interesting. It looks better than you might think at first. It does have kind of a bad history. Everybody said, "Oh, that's terrible." And there is a textbook, which I actually have a copy of, and he clearly says the hybrid airship combines the disadvantages and loses the merits of both types. And that was back in 1927. I'm not sure he's completely right there. And maybe he's thinking of that Tom Swift book and some approach like that. But in any case, this is not the first time people have proposed this. So if we want to be successful with it, we better understand the problems that people saw before and solve them or reason to come up with a reason why they're really not that important. Okay, so anyway, the very first thing to do, though, is to stop thinking of this as an airship with wings. It's not an airship with wings. Think of this as a regular airplane that gets some lift from helium bags. Okay, if you kind of rethink the paradigm, you'll get closer to understanding how this thing actually works. Okay, it's not an airship with wings. Just looks like an airship with wings. All right, now when you do the analysis of this, I've found that I can analyze it mostly like a normal airplane. As I said, the usual drag calculations work. They're a little conservative, a little pessimistic, so I find knocking it down by about 15% seems to give me pretty good answers that track with wind tunnel data. You probably have to assume 100% turbulent flow because it's so big that on a percent basis, it's pretty much all turbulent anyway, but you get a benefit from the Reynolds number effect. So it hurts you because it's all turbulent, but you do get a Reynolds number effect. Okay, let's see. You don't need as high of a lift coefficient or a smaller wing. You need less aerodynamic lift. You have to take that into account. So the normal lift to drag calculation is shown here, and where it shows the weight term, that's the wing loading W over S, you just reduce the weight by the amount of gas lift. I mean, that's very easy. And then you take that and you stick it in the Breguet range equation. So what could be easier? It's easy. But when you're integrating the change in weight, you don't use that. You use the full weight for that. That's a little bit confusing there. And also, as I mentioned before, you do have to take the total mass when you talk about accelerations. And if it's a climbing acceleration, yeah, you have to take the total mass, which includes the mass of the gas you're carrying. So this gets a little confusing, but not that bad. Estimating the weight of the vehicle, you sure can't use any classical airplane methods other than perhaps on a component basis. Like you can probably estimate the weight of a wing if you make the right assumptions, using kind of classical aircraft wing statistics. But be very careful. Those statistics, they usually have a velocity term in there. And if you use it for slow speeds like an airship or a hybrid airship, you're out of the credible range of the data. Anytime you have an empirical or a semi-empirical equation, you don't want to apply it to a case far away from the normal data. So watch out for that. Well, I could go into more detail on that. I think I've come up with a reasonable way of estimating it, but much better to get some pretty detailed calculations as soon as you can. Okay, so that's what I wanted to say about the hybrid airship and how it works. Some methods that I've found work reasonably. I have been able to use my RDS aircraft design software by playing those games that I showed you before of changing the weight. So I'll do the calculation, and for some of them, I'll make the airplane weigh half as much, and then I'll come back for other calculation and make it weigh the same. If I was doing a whole lot of this, I'd probably put in some kind of a adjustment built into the code, but don't do it that often, so it's more economical to just sort of think my way through it as I'm doing it. Okay, well, that was kind of the background I wanted to go into, and now I have some information about two designs. And like I said, Bob Rist of Ohio Airship was kind enough to tell me that I could just show everything. He's not actively pursuing it now. He's very proud of what he did, and I'll show you some of what happened, but he isn't funded right now and he's not actively pursuing it. He might start again, but in any case, he's very kindly given me permission to use all this stuff. So it was a project. He started a company called Ohio Airships, and he was pretty well funded by an elderly gentleman who was quite wealthy, and his brother, the elderly gentleman's brother, had been one of the last US Navy blimp pilots. And he sort of, as a memorial to his brother, decided to fund Bob Rist and his Ohio Airship Company. And that's really where the funding came from. Some other sources of funding, but the main funding came from that. I got a telephone call out of nowhere from a guy named Bob Rist, and he asked me if I know how to design airships. And I said, well, no, not really. And he said, sort of, pretty much, well, I'm going to give you a contract anyway, figure it out. So that was when I started digging through all the airship books and refreshing my memory on Charles Law and Boyle's Law and all that kind of stuff. But anyway, that was, I don't know, 15 years ago or so. In any case, we went pretty far with this, and it is an interesting idea. So Bob's basic vision was a hybrid airship. He didn't ask me to generically solve some transportation problem. He wanted to do a hybrid airship, and he had some ideas, especially for the structure, and he had a patent on it, actually. The idea is for like an internal structure. You can see it in that top right drawing. There's a keel right down the middle and a bunch of frames, and it's all supported by wires, crisscross wires of various sorts. So he had that patent, and he showed me his patent, and it actually looked pretty good for this type of thing. And so I designed an airship around that basic idea. I did a lot of calculations. I'll show you those in a bit. It turns out that it's optimum if you're right around 50-50 on lift, at least for this application, about half the lift aerodynamically and half the lift from the helium. It does take off and land, wheels on a runway. It's got to be a pretty big runway in terms of width. It's a big vehicle. It doesn't take that much length to take off, I'll show you, but it's a big vehicle. There's different versions of this I designed for him. This is the main version. It's about 1,000 feet long, 300 meters or so. So this is quite a large vehicle, but on the other hand, it carries a lot of cargo. Okay, so that was the basic idea. This was not lighter than air. It's about 50-50. Takes off and lands, wheels on a runway. The hull is carefully integrated with the wing. And what you really want to do to minimize drag due to lift, you don't want a lot of lift from the hull. You want just the right amount. And the right amount is to keep an elliptical lift distribution. So when I designed it to get some lift on the hull, but not too much. You don't want too much lift. And we later did CFD, and I'm proud to say I just about nailed it. Just about exactly the right amount of lift came from the hull. And like I said, we used this patented structural concept. So these are some of the charts that go back to the Ohio Airship days. A little bit redundant with what I showed before, but let me just show you how it was presented for Ohio Airship. So number one operational advantage, no airship mooring, no mooring mast, no ground handlers, no heavy guys grabbing it, no worry about the thing tipping over and all that kind of stuff. So it's primarily a reduced operations cost. And that's a real benefit compared to a normal airship. It's going to integrate better into an air traffic control system, mostly because it flies faster and it does a takeoff and landing on a normal runway. It has a smaller on-ground footprint than a regular airship because you don't have to worry about weathercocking. You don't have to have a radius all the way around a mooring mast, which is a huge area. You can park it and set it somewhere, and it's basically an airplane as long as the wind doesn't get too big. It can tolerate a substantial side wind. That actually turns out to be a design constraint. I'll talk about that in a minute. And it's sitting on the ground, so you can have aircraft-like loading and maintenance. What Bob asked me to design was a vehicle that would be a heavy cargo lifter with a huge cargo bay. And that turns out to be a pretty good application for this thing. More advantages, there's no venting or refilling of helium. It has ballonets. You don't have to worry about it. Just normally like an airship. No ballast. We don't have that problem. Some airships have ballast, and when they're having a really tough day and they're maybe getting pushed down by wind, or maybe they're heavy because of they got some rain or something, they can drop sand or water. You don't have to worry about that. You just increase angle of attack of the wing. You don't have to weigh it off. I didn't mention that, but when you're going to take off in an airship, you need to make sure that your lift equals your weight, so you have to add up the weight of everything you're carrying and make sure that it fits. We can also trim aerodynamically. We don't have to move helium around to trim in pitch. No problem with the weight impact of fuel burn off. And also you can land with a large loss of helium. In fact, I think you could land it without any helium if you lost everything, because you do have 50% lift. Basically, you just have to land faster and hopefully have a pretty big runway, because it'd take a while to stop. But yeah, you could land it with no helium at all. Okay, the technical advantage in terms of aerodynamics, the key one is that you get a very good lift to drag ratio, but it is at quite low speeds. So this is kind of an interesting chart here. The left axis is lift to drag ratio. The horizontal axis is the percent of lift that you're getting from gas. So it's the gas lift divided by the total lift. So over to the right would be 1.0, and that's a pure airship. Over at the far left off the chart would be 0.0, and that's no gas lift at all. So that's a pure airplane. And this shows you kind of what happens. And then the different curves are the velocity. So you can see what happens here at a very low velocity of 60 knots or so. As you get more of the lift from gas, you get crazy good lift to drag ratios. You can get up around 40, 50, 60 lift to drag ratio. Whereas when you go faster and faster, it actually gets worse. What's going on there? Well, more gas lift means a bigger gas bag, which means more parasitic drag. So this kind of guides everything you need to think about if you're looking at a hybrid airship. So you want to fly slow to get the efficiency. But on the other hand, compared to a regular airship, you can still fly pretty darn fast. So that really becomes kind of a big trade-off, a big design criteria. Okay, I'll talk about this some more. We talked about the airship, hybrid airship, all the good stuff. Here's some of the bad stuff. First of all, the structure has to take aircraft-like landing loads. You hit the ground, everything flops down like that. Everything inside has a downward momentum, and of course that's something a normal airship doesn't see. So you need some good structure like that internal structure Bob Rist is talking about to take those loads. The wing loads and the landing gear loads are quite concentrated in structure. You've got this big lift load that has to go into the airship structure, and airship structure usually is very lightweight. So that can be a big weight impact. You have to worry about side wind. So you have to basically design it to withstand a certain side wind. And I'll talk about that. You don't normally worry about a big commercial airliner, a Boeing 747 sitting there. You don't worry if you get a 40-knot side wind, big deal. A 100-knot side wind wouldn't hurt it, let alone a 40-knot side wind. But for something like this, yeah, you have to worry about that. It's going to be very large physically. Anti-icing the large hull is quite an issue, and there's different schemes for it, including a pressure pulse applied from the inside that might break the ice off. Of course, you could just use wire heating, but it's huge. That's a whole lot of wire, and that's a lot of wire weight and a lot of electricity required. Let's see, inspection and maintenance of the helium lifting system. That's all stuff a normal airplane doesn't have. It's not real bad in terms of inspection and maintenance, but it's not nothing either. The weight of the structure is going to be up because of the higher speeds and those extra loads compared to a pure airship. And you do have more manufacturing and support costs. It's a big thing, so you have to worry about that. So there are disadvantages. It's not all advantages. All right, now I started the design process, and one of the first things I wanted to do is look at the cross section and basically the aspect ratio of the cross section. But I have a completely round circle, which has a lot of structural efficiencies, or would I flatten it out? Well, why would I want to flatten it out? Well, if you flatten it out, you get more lift on it, and that might be a good thing. But more important, if you flatten it out, you reduce the wind side force. And that's a big thing. So when it's sitting on the ground, we'd like it to sit without having to be tied down like attached to a mooring mast or something. You don't want that. So it's a good thing if we can flatten it down a little bit, because you do reduce the side load. So I started looking at that a little bit. And let's see, this is pure geometry here. So reduce side load to the right, but it's also higher drag and volume that way. Looking at this, sort of looking at the knee of the curve there, the height versus a regular circle height, as you can see, it gets better real quick. And then it kind of flattens off like a lot of things do. Whereas the increase in wetted area, it kind of kicks up a little bit, but then it continues pretty much linear past that. So it seemed like the thing to do is to not flatten it too much, just take what credit is almost free. And it looked like a little bit less than 1.5. And for reasons I completely forget, I decided to go with the square root of 2, 1.41. So that's what I used for the design, and it actually seems to be a good place to be. I stuck with that. It seems pretty good. Okay, so then with the assumption of a square root of 2 ellipse, then the question is, okay, what is the best number to use for the percent of gas lift? The more gas lift you have, the better the lift to drag ratio at slower speeds. Of course, we saw that, but it also tends to limit your high speed. But the issue I wanted to look at first was this issue of the side force on the ground. So you're sitting on the ground, you're getting blown sideways. If you have a very large hull, then there's a whole lot of area. And so you get a large side force. And if you have a lot of gas lift also, you don't have much weight on the tires. And the friction you can get out of a tire depends on how much weight is on it. I used the sliding friction rather than the static friction. So what I'm doing is I'm saying, I want to make sure that even if there's a steady large wind and I get pushed and it starts moving, I want it to stop moving. So it's not just the static breakout. I want it to actually slow itself down and stop if it does start moving. And so came up with these two curves here. And the blue one shows that as you get more and more gas lift to the right, you have a bigger hull, so you have more and more side force. The red one coming down from the left is the sliding friction that you get. And as you go to the right, more and more gas lift, there's less weight on the tires, so you get less. So look at that, it crosses just under 0.5. And so I kind of foolishly said, well, I'll just use 0.5. We don't know any of these very accurately, so I pick a round number. And that was foolish because ever since people have assumed that 0.5 was just a guess or some magic assumption, it's a round number. It sounds like I just made it up. No, it's actually based on this analysis. And it really should have been about 0.47, which is probably what I should have used. Okay, but I actually used 0.5. So with that, then I did a layout. I'll talk about it later. I started out with some preliminary calculations. I wrote a little spreadsheet to put this stuff together to try to estimate the whole volume based on the lift. And I won't go through all the calculations. The design approach looked like this. I did use a flattened ellipse. I actually flattened the bottom more than the top because the lift is pushing up at the top. So that's where the force is going to be. So I kind of flattened the bottom, and this also brings the thing down lower to the ground, which I want, and it also reduces the side force some. So it's a flattened ellipse, and it's more flat on the bottom than the top. I deliberately shaped the hole with a little bit of camber. I actually used a typical airfoil. I forget which one of the slightly reflex trailing edge airfoils, because I didn't want to get a big pitching moment. I used this airfoil center line and basically shaped my hole around that, and it worked quite well. If you'll notice at the back, I flattened it out and made sure it lined up with the horizontal tails. What I'm trying to do there is I'm trying to trick it into giving me a good CUDA condition at the back to get lift on the hull. And again, that seems to have worked. Vertical tails, one on each side, trying to get good air on the tails, but also making it nice for bracing. So I could brace all the tails, kind of cross brace them with each other. As I started going through this, I realized I was going to have a lot of trouble with center of gravity because the tails are a lot heavier than anything in front. And it has to balance both hydrostatically and aerodynamically. They both have to have center of lift just about through the center of gravity. And I couldn't make that work So I came up with the idea of putting 2 of the 8 engines in the front. And I also decided I really needed a canard for no other reason than to rotate for takeoff. This thing is 1,000 feet long, and I don't want to rotate the nose up just by pushing back on the tail. So I included the canard to rotate for takeoff, but I'll get lift off the canard also. And the canard is so far away from the main wing that the usual interference problems that make canards kind of a bad idea often, it's not very important. It's so far away. So that's the basic idea. Everything, all the systems and such were commercial off the shelf. So that's the basic idea. Here it is. It's 990 feet long, about 300 meters. Gross weight of 1 million pounds, payload weight of 350,000 pounds, or about 1/3 of it is payload weight. If you look at this side view drawing, in the very front of the hull, there's 2 little tiny specks. It looks like I spilled pepper on there. Those are the pilot seat. It's a big vehicle. And I originally assumed I'd put the pilots up in the nose so that they could get a good view. I figured they'd probably force me to do that. The FAA would force me to do that. But that's not where I really want them. I really want to put them in the front of the hull. And I think today everybody would accept that you could use cameras up at the nose and not require the guys, the pilots, male or female, not require the pilots to make such a long hike. That's a long ways to get up there to the front. So they're going to be back in the payload bay. It's a very large payload bay, by the way. Let's see, this shows the structural concept. There's that center keel, which is actually a triangulated, it's 3 tubes triangulated. And then you can see there's sort of structural towers that are triangulated to pick up the wing and canard loads and spread them nicely. And then there's some additional towers, nose to tail. You can see it in the side view. And then there's a lot of triangular bracing there. So that's the basic structural concept. And it seems reasonably credible. This is a cross-section view with all the triangulation. On the top right, you can see how I would pick up the lift loads with straps that would go from the center and out to the tip, sort of like almost like the mast of an old sailing ship. You could basically hold on to the skin all the way along it with these triangulated things. Down at the bottom are ballonets, and yes, there be ballonets. And finally, at the very bottom picture, that shows how I'm going to attach that tape group. So it looks like it works. This gives you a size comparison with a 747 and a C5. So this is a big vehicle. And having one of these things land at your local airport is probably going to be difficult. So this will go into major airports. And you'll need some pretty big parking places on the ground for these things. So that's part of the problems that need to be solved. You're not going to take this into a little airport somewhere. Okay, here's an interesting comparison after I did all the calculations. The motor I selected is actually the T56 turboprop, and it's the same one that is in a C-130. I needed 8 of these motors to get the speed I wanted. So I have 8 T56 engines, which is the same as the engines in 2 C-130s. So how do I do compared to 2 C-130s? Well, compared to 2 C-130s, I have 4 times the payload weight of 2 C-130s and 12 times the payload volume of 2 C-130s. And it's about the same or even slightly less operating cost as 2 C-130s. So it's kind of interesting. The problem, of course, is it's flying very slowly. And so if you're carrying cargo somewhere, you don't get there as fast as if you send out 2 C-130s. So, the applications for this have to be looked at very carefully, and you need to do a complete system study to see if this really is a better way to haul cargo across the ocean and things like that. That's the thing that a lot of enthusiasts forget when they look at airships. They forget the fact that you have to take time into account. And the real measure of merit isn't how much it costs to carry a particular payload across the ocean. It's how much it costs to carry a whole bunch of stuff over a period of time across the ocean. And if you have a vehicle that flies very slowly, then it's going to take longer, or you'll need more vehicles to get it across in the same time. Okay. All right, so I went through a typical analysis. These are classical methods, like I said, adjusted based on old airship data and some wind tunnel data. We did get in the wind tunnel. I guess that was Purdue, wasn't it? I think it was Purdue. I should know. I I used to work in that wind tunnel. I went to Purdue. In any case, maybe it was Ohio State. Anyway, one of the Big Ten schools put it in the wind tunnel as a student project. And they pretty much matched the aerodynamic data pretty closely to what I was predicting. So that's good. We also ran computational fluid dynamics. I had analytical methods in Seattle, run the VS Aero code, which was, pretty good code back in the day. We have much better things now, but it looked pretty good. And we showed with this that we got a pretty good lift distribution and a pretty good drag due to lift, actually. It worked out pretty well. We did look at structural analysis. I hired a company called Composite Engineering, and that's now Kratos. They're very well known now as a producer of jet target drones. That was in the early days, and they weren't in production yet. They were developing them, and I was actually helping them with their target drones. So they hired me, and then at about the same time, I hired them to help me with this airship project. And they concluded that this could best be made out of graphite composite tubes and truss structure. So they'd go into production with the standard diameter graphite tubes and come up with some fittings. Today, we'd probably 3D print the fittings. Back then, they were going to mold them. And then Kevlar straps to hold the whole thing together. So that seems like a pretty good idea. They were going to actually pultrude those tubes. Anyway, so they went through a pretty detailed weight analysis, and I took their numbers and refined my predictions. This is the T56. I didn't have good thrust data, but I did have good power data. So I took that and applied it to a standard propeller model in my RDS software. That's all right. So I went out and ran a bunch of calculations. Here's a takeoff distance. And of course, the normal takeoff weight is to the far right here. It's the 1,000,000 pound. So if you lose an engine, it's the worst distance, and it's going to be a valid fill length of about 4,000 feet. So that's pretty short takeoff. That's not bad. To that, you have to add the length of the vehicle itself, which is another 1,000 feet almost. Same thing with landing, a little bit better than that for landing. And I did rate of climb. It doesn't have a very fast rate of climb, but it doesn't have to climb very high either. You're not cruising at 30,000 feet. You're cruising at about 10,000 feet. And I did an optimal climb trajectory, and it looks like just take it basically to 100 knots and hold 100 knots all the way up. It seemed about a reasonable optimization. And then I did a range calculation. I'm getting about 4,800 nautical miles range out of this thing. So it's definitely transatlantic. You'd have to island hop to go trans-Pacific. And a bunch of other calculations. And this is all just airplane design stuff, so we don't need to see this. Payload versus range. When you offload payload and put in more fuel, of course, you get more range. And if you actually had the extra tankage required, you could get out to well over 6,000 miles range by having less payload. And I did a bunch of trade studies, dead weight, sensitivities, just to see how sensitive it is to some of the assumptions that I made. And it looks, they're all sensitive, but it doesn't look insanely sensitive to anything. Now, Bob asked me to do a mini version, a little tiny dynalifter. And so I did. So I scaled the whole thing down to a 2-man dynalifter with a 2 engines. Now, I'll mention that in a bit, but just realize when you scale something like this down, the volume goes by the cube of the dimensions. So you lose volume fast when you make it smaller. This is the square cube law that people talk about. So it's always a difficult thing when you scale these things down and make it small. But I was able to get something that would work, about a 2,000 pound total weight, a 2-engine vehicle, looks something like this. And guess what? He built it. Built it. Not exactly as my layout. He changed a few things, but he pretty much built that about that size. And he built it more as a proof of concept. He wasn't really intending to fly it because he didn't have enough funding to do the full analysis and flutter testing and all these other expensive things. But he built it to be, a completely functional vehicle. He just didn't do all the things that would be necessary to get permission to fly this thing. And he was hoping that with this built, that somebody would get excited and would give him enough money to either build another one or modify this one, do all the analysis, do all the testing necessary to get clearance to fly the thing. But he did build it, and there it is with the wings off, but he later put the wings on. I'll show you in just a second. It got the cover of Popular Mechanics, That's always fun. I've had a fair number of my designs on the cover of these magazines. It's always exciting to see it. I got a kick out of this particular cover. It says return to the airship. That's good. And just below that, it says smarter, safer. That's good. And then way below that in big letters, it says 5 mega disasters. Of course, they're not talking about the airship, but it's pretty funny. Anyway, that's me, by the way, in the bottom left there, sitting in it. It's not completed yet. There was a fuselage that went around that. But anyway, long story short, he built it. It actually later got damaged by the wind and he didn't have the money to rebuild it. And the last I heard, I think the parts are in storage somewhere. So unfortunately, it's not in this shape anymore. But it actually did fly. It wasn't me and it wasn't Bob, and I'm not going to tell you who it was, but he had a pilot that was supposed to do a runway test. And like a lot of pilots, apparently he just couldn't resist seeing what it would do if he pulled the stick back. And the answer is it flies. So there it is. And if you look where the pilot is, he's actually pretty high off the ground there. The tail's almost touching, but it's 120 feet long. Anyway, it flew no sweat, had plenty of control and nothing wrong. He didn't get much higher than this, just flew it down the runway and then chopped the power and landed it, but it all worked. Okay. And by the way, if you're interested, the story of this design is in my memoirs book, Living in the Future. There's a whole chapter about this, and it was a fun project. You're welcome to get a hold of that and read it. All right, so that was the Ohio Airship Dynalifter, and now I'm going to talk about James Egan's idea, which is, he calls it PLIMP for plain blimp. And again, he contacted me, and by that point, I already did know something about designing airships, so we didn't have that conversation, but he contacted me and said he was very interested in doing a hybrid airship and wanted me to do the layout. He had some ideas and some pretty firm requirements. And one of those requirements is quite different from the Ohio Airship project. That requirement is vertical takeoff. And that changes a lot of things. It makes it more difficult to do a hybrid airship when you also require vertical takeoff. And we didn't do that in the Dynalifter project. In fact, there was a DARPA contract that we bid on, and DARPA asked for vertical takeoff, and we said no. We showed some ways it could possibly be done, but our calculation said it would sort of make the whole concept very difficult to do successfully for that scale of vehicle. And James Egan wanted it for this one, but it's a whole different class. It's a whole different requirement. It's not a long distance cargo carrier. So it's a little more feasible, and it looks like, in fact, for this, it does work. And in fact, it's flying right now in subscale form. Anyway, so vertical takeoff was a requirement, electrical power preferred. And one of the things that kind of drove this a bit is the desire to be able to transport this thing and break it down and transport it. And for some applications, that's very useful. UAVs, for example, surveillance UAVs. It'd be very nice to break it down, put it in a box and ship it somewhere, take it out and get it flying real quick. And so to address that requirement, what I did is I worked hard to separate the airplane stuff from the lifting envelope. And you can see that there's a number of different versions, different scales, different applications, but they all kind of look the same. And you'll notice that the lifting bag doesn't have anything on it. It doesn't have big tails at the back. It doesn't have wings sticking out the side like that winged airship I showed earlier. So there's sort of airplane stuff underneath. It's almost like a funny looking airplane that somebody stuck a big bag on the top. And that's kind of what it is. So that's sort of the basics of this approach. Bob was kind enough, I'm sorry, not Bob, James Egan was kind enough to let me use illustrations that have already been shown publicly. There was something in the UK Daily Mail newspaper and article online. So you can find that. It's interesting. It's got more detail. But in any case, that was the basic idea. And there's quite a few applications for this thing. Here's another illustration. James artists are good artists, and they took a little bit of artistic license. I didn't do that long, skinny window in the front. That would be too heavy, but it looks really cool. But mostly it's the design that I came up with for James. Possible applications, various surveillance types. Being that it's a hybrid airship, it's quite a bit faster than a normal airship. And that's sort of the market niche here. It's a airship-like vehicle, but being a hybrid airship with powerful propellers, it can go quite a bit faster. So it can do search and rescue, agricultural monitoring, power line, a lot of things like that, just surveillance, reconnaissance type things. And there's various military applications that could be of interest, of course. So that's kind of what the plimp is intended to do. And I can't say much more about it, but I'll close this with a cool picture. That's James Egan on the right and his twin brother Joel on the left. The two are kind of the founders. James is kind of the lead guy. Joel's involved also. And at the back is one of, I think that's the third or fourth demonstrator that they've had built. And the people that have made the demonstrators have moved a little bit away from the configuration that I had, but it's just the same basic idea. And there are videos online showing this one and I think another one flying. And it's really quite interesting. It moves pretty fast and it's quite maneuverable, very controllable. It's quite a cool looking thing. Anyway, James is continuing to pursue this. And in fact, I am trying to clear my schedule. I have a DARPA final report to write. And when I get that out of the way and then a little bit of rest and relaxation time, then I'm going to jump in and design another version for James. He has a customer that's quite interested in a vehicle that would have certain characteristics. So I'm going to do a design study and we'll see if that one looks like a good approach. So anyway, that's what I wanted to say about the Egan airships. And now let me summarize a couple of thoughts, a couple of suggestions here. So here we go. First of all, a hybrid airship seems to promise better operability than a true airship. I think that's true. And you can get better lift to drag ratio and lower fuel consumption than a true airplane. So there's sort of an intersectionality there. There's a spot between those two that looks interesting. And with a little bit of luck, you can find a good application and a good vehicle that meets it there. Design and analysis does seem to be more like an airplane, but you do have to start with all those lift calculations and the envelope design. And we talked about that before. There's a lot of detail on the envelope design, and I'm certainly not the expert in that. We talked about ballonets. You have to carry the loads internally. So you have catenary curtains, which are basically fabric or whatever material, mylar, hanging down, and you tie strings to it, and that's how you transfer the load. And there's just a whole bunch of other things on the actual envelope design. The square cube law is not your friend. And I keep saying this, a bigger envelope is better. If you want to do a little tiny vehicle that flies around inside your room, a little toy airship, you don't get much lift from that. Whereas if it's 1,000 feet long, yeah, you can get a lot of lift out of something that big. And it's the square cube law thing. If you double the length, you get 8 times the lift. Okay, the next two are really quite true. As you're doing a hybrid airship, if it gets too blimp-like, if you get to the point where most of the lift is coming from the gas, there's really no benefit from all the extra airplane stuff. You get rid of it, just do a blimp. So you have to watch out. You don't want to get way up there in very high level of lift coming from the gas because you can get everything you need just by putting a propeller out on a stick somewhere. You don't need wings and that sort of thing. The converse is true. If it gets too airplane-like, if basically almost all of your lift is coming from wings, then the blimp part just adds drag and complexity. So it's going to be somewhere in that middle sweet spot, driven by things like whether it can sit on a runway in a particular side wind and other aspects, things like trying to optimize the drag. Just watch out for this, though. Don't let yourself get pushed to either extreme, because if you get near either extreme, just go away. Okay, one caveat. I like hybrid airships. I'm interested in them, and I've been involved in the design of several of them. I'm not convinced. I'm not ready to say that they're definitely better than either a blimp or a regular airplane for any particular application. I don't know that. If somebody came and asked me to meet a particular customer need and they didn't care what kind of vehicle it was, I would include that in the early trade studies and try to decide if it was the best. I wouldn't walk in saying, yep, it's definitely the best, because you just don't know. It might be, maybe a helicopter is better, maybe a pure blimp, maybe an airplane with a big wing. There's a lot of different ways of skinning a cat. So I'm not sure which one. And I can't stand up and say, yes, for sure, a hybrid airship is better for this. But on the other hand, for certain applications, it could be a useful option and it might be the right answer. So it sure is worth a trade study. And that's it. And look at that. It's just about exactly 90 minutes. So there I am sitting in there. And I probably would have flown it if he'd let me, even if I would have killed myself, just because it would have been so cool. Anyway, so I'm done. Any questions?
Yeah, excellent, excellent. Very nice. Really interesting. I mean, very thought-provoking, like always your talks are. Yeah, let's open the floor to the audience for asking questions. Yeah, we have good time available.
Hello, Professor, Dr. Raymer. I'm Sohan Suvarna from LTA lab, Professor Pant's lab. So it was a very nice talk, and particularly the Eagan Airship one, because ever since it was the first news, it had made the news. I had been following the updates on that, and particularly because I work on the dynamics, and it kind of intrigued me because it combined the good characteristics of airships. That's the buoyant lift. And also had the stability features, which was the vertical tail and the horizontal tail, which was kept at a certain momentum. So yeah, it was really nice to get an update on that as well. Now I wanted to, so you pretty much answered all the questions that I had during your sessions through your slides. So one thing which spiked my interest was on page 56. That was a magazine cover, and it also said safer nuke power in the airship. So I was just wondering what that meant.
Number 56, you said. Let's see if I can quickly find 56. Is it this one?
Yes. So in the poster, in that magazine cover, smarter and nuke power.
Oh,
I was joking. Everything below the airship is other articles in that magazine. I was making a joke. I got you. You fell for it.
Okay. Okay, so my other question is, there has been a lot of debate between conventional airships, hybrid airships, and even lenticular airships. So one of the, just being a devil's advocate here, so one of the comments that come from people who like conventional airship is that it's particularly very difficult to land a hybrid airship, especially because you have static heaviness. So it means that there would be additional loads while it comes to land. Secondly, the added mass factors. So because it has a larger projected vertical reference area, so it means it would be a little more unstable as well in terms of pitching. So that's one comment. And the second comment is that there is a huge wetted area for hybrid airships. So which means that there is a larger drag as compared to a conventional one. So what would be your answer to that, sir?
Well, I of course included that in all the calculations. Looking at the extra wetted area, yeah, but remember the hull gets much smaller. The gas bag gets much smaller because you're only carrying about half the weight. So you actually wind up with a less wetted area for a hybrid airship for the same total lift. So that part is not an issue. As far as the stability, it's just a matter of making the tail the size you want. And for any modern airship, I'd make it a relaxed stability. I'd make it an active flight control for any substantial vehicle. For something like the plimp, where you are doing a vertical takeoff, you do need to add control, powered control. So you can vary the thrust from side to side for roll, but you have to have a tail rotor, either a single tail rotor that can rotate about a longitudinal axis so you can get pitch or yaw out of it, or you need two of them at right angles to each other. And then once you put those tail rotors on it, then you've got plenty of control at lower speeds.
Thank you, Dr. Raymer. It was really a very nice talk. I enjoyed it throughout the session. Thank you very much.
Oh, thank you. You ought to see the plimp come in for a landing. It's the easiest, nicest thing in the world.
Yeah.
I think I can add to this without James killing me later, but the first one was flown, and it was a rather large subscale vehicle, and it was flown in a facility between storage buildings and in a parking lot. And the guy just put it right, he took it off just pretty much straight vertically with cars and trucks on both sides, and flew all around, no problem, and came back, swung it around, pointed into the wind, just dropped it right in place. Most beautiful thing you ever saw. So at least that one has beautiful control for landing. And then it sits on the ground when you turn off the fan. So that's, that part's really good.
Yeah. So I'm actually intrigued by the plimp concept, but I understand that I cannot ask a lot of questions. But so I'm keeping those questions to myself, and maybe later on I could discuss somewhere.
Well, who knows? Maybe some kind of a teaming arrangement could be worked out with James Egan. I'll leave you guys to discuss that.
Sure.
It is an interesting project. Yeah. Okay. Thank you for your comments, and very nice to talk to you.
Thank you, Dr. Raymer. This is James Egan. I was asked to.
Oh, hello, James.
And I wanted to say, yeah, thank you. What an amazing presentation. You're really covered a lot of interesting stuff. I appreciate the years that we've worked on this, and the design that you created for the plimp is pretty interesting. You mentioned a video. If anybody wants to reach me, you're welcome to do that. And we can talk further. I can probably show you some other videos. I'm at james@plimpairships.com, and I can send that email over everyone so that you can do that. The designs that have flown, there's been some iterations, and we've gone backwards a little bit. At the same time, it taught me something, which is that the Raymer design is a pinnacle design. The purpose, when I asked Dr. Raymer to design this, was to have vertical takeoff by rotating the wings or rotating the nacelles. It was actually something that I think Dr. Raymer came up with, but it was something I roughly envisioned. And I had no particular idea of what it would look like. I just said, look, I wanted to have vertical takeoff and landing. I wanted to have highest speeds for an airship, a hybrid airship. And it does appear to have some pretty high speeds. The at least on paper by Dr. Raymer's design, this Model A version that you look at, kind of like this, could be 91 feet long and get to, I believe it was 120 miles an hour at really high speeds. The other advantage, I think, is slow descent and controllability. It banks on turns. So if anybody wants to see videos, sure, you can look on YouTube. You can look at the website. James at plimpairships.com is my email. And I did actually have a question. I'm not going to dominate this. This is Dr. Raymer's expertise, which is that one of the benefits that some of our potential customers are seeing is a stable platform, which is why there are blimps used in the military, for example, border patrol, that kind of thing, picking out images at very long ranges. And I guess my question is to Dr. Raymer, to what extent do you lose stable platform filming at a 50-50 ratio versus, that is 50% lift by helium, 50 by other, versus 100% buoyancy, or in the case of a plane 0%? Where does it start to diminish, if you can opine about that? And maybe you'd need to do some trade studies on that. But
off the top of my head, James, that would mostly be driven by the speed you're at. If you want to do that while you're going quite fast, then a wind gust is going to give you a big change in lift. But if you keep the speed down, then it would still be pretty darn stable. And let me tell everybody that 120 top speed, that was based on a lot of assumptions. It's not every one of these things gets that. That was kind of a special calculation. So don't think that all plimps go 120, please.
Right. No, it depends on the size. You're right.
Absolutely. I don't want to get them all excited.
Mm-hmm. Well,
Yeah, okay, well, great, James. I'm glad you could join us. I think we better let some other people ask questions.
Sure.
So, yeah,
Thank you
but
so
I'm really
much.
glad you could join us, and thanks for letting me use the material.
You bet.
And really, James would be delighted to share more things with some of you. So send him an email if you're real interested. The videos are fantastic of the subscale models flying. It's fantastic. Okay, any more questions?
Sir, good morning.
Hello, sir. Yeah.
Myself, Raju.
Yeah.
Sir, I am from Anna Saheb Dange College of Engineering Technology, which is in Maharashtra. Sir, actually, it was a wonderful session. I am happy to attend this session. And I don't have a particular question. I would like to get 2 comments from you about, let's say, me kind of amateur designer. If I am going to design one airship, what would be the major one thing? I know that it cannot be converted as like one thing or 2 things to be very careful about. But if you say, as by your experience, like, Raju, be careful about this point when you are going to design one airship. And the second part of my expectation is, what will be your comment about multi-lobed airships?
I'm sorry, I didn't understand that last thing. Would you please say it again very slowly? The connection isn't real good.
It's multi-lobed envelope. Multi-lobed envelopes.
Okay, multi-lobe envelopes, you're saying. Okay, sorry. I didn't talk about that. I know there's been a lot of work on that as a way of getting a more aerodynamic lifting shape. I don't know. Those are still big floppy blimp kinds of things. And I just haven't done a design where that seemed like the way to go. You get a lot more wetted area, which means a lot more envelope weight for the enclosed volume. But if what you're trying to do is have a blimp-like vehicle with good aerodynamic lift, then I guess it makes sense. But that's not the way that I went with either of the designs I was involved in.
Yeah, so Dan, the answer to this question is in the next presentation by
Okay.
Mr. Manikandan is working on this towards his PhD, which he will hopefully complete very soon. Okay, so
well, I'm glad I didn't say they were bad. I just haven't worked on those before.
Okay, a gentleman.
Thank you.
Yeah,
thank you so much, sir.
Thank you, Riju, for your question. A gentleman.
So I have one question, sir.
1 minute. A gentleman by the name Rich Hollowman has a question on the text. So maybe we can ask him to just unmute and speak. If not, then I'll read out the question. Okay, so his question is, how about shape-shifting variable buoyancy envelope, much like how fish, like pufferfish, move in the water, thanks to advances in materials and compliant mechanisms engineering?
That sounds great to me.
Yeah.
Show me the mechanical engineering part of it, but it sounds great. I just don't know how to do it.
Yeah. Okay. So Dr.
Variable buoyancy is a question that comes up a lot. And I talked about it a little bit when I talked about compressing the lifting gas. That's one of the ways of getting variable buoyancy. But I haven't seen something in that field that looks to me like an engineering solution, but I'm very eager to see it. I just haven't seen it yet. Maybe it's out there and I haven't run across it, but nothing I've seen looks like a workable engineering solution. But to vary the buoyancy, you got to change the density of the gas or the volume of it, or the temperature or something. I guess you could take helium and heat it up. That would change your buoyancy. You could fill the ballonase with helium or hydrogen. You know, there's different things you could do, but I haven't seen a real clean engineering solution yet. If there is one, by the way, send me an email. Point me to somebody. You know, point me to a good answer, a paper or something where somebody's getting variable buoyancy to work. But I just haven't seen it.
Okay, so we'll move on to Dr. Manish Tripathi, who has a question, and then the next one will be Palniappan.
Hello, sir. Sir, firstly, I would like to send my regards for the presentation. It was a really thought-provoking presentation. And in fact, I would even rate it to my top position based on all the presentations that I've attended till date. So a lot of new sites into airship designing and hybrid airship designing was given through your presentation. Thank you very much for this presentation, sir.
You're welcome. Would you like-
So basically my question is like, for instance, in this Egan airship design, so you have made use of 3 propellers I can see, 2 in the front portion and 1 in the rear end. So was there any basic science behind selecting this, whether it was based on aerodynamic aspects or some stability aspects?
It's actually 2 propellers. What you're seeing in the back is a steering propeller. And that's one that can point in all directions. So for forward flight, you might do this. You might point it in the flight direction and turn it on or let it windmill. But when you're at low speeds, this particular one would be perpendicular to the flow. And you'd rotate it around a longitudinal axis like this to get a vector pointing in the direction you need for either pitch control or yaw control or some combination of those. So the actual lift is coming from the 2 propellers on the tips of the wings, and they're on the tips to get them as far outboard as possible, to get them away from the hull. And a couple ways of doing this. The designs that I've done all have the entire wing pivoting, just because that's mechanically easier. And it's slightly forward swept so that when they're pivoted, it's further off the ground. If you figure out the kinematics of that, it actually lifts it off the ground a little bit more. And it also puts the pivot behind the passenger compartment, which was an issue with layout. So that's basically how that came along. But there's a bunch of other ways of doing it. And the guys that made subscale models preferred to, well, one guy put it on the wing, but only halfway out. And the other guy put it on the wingtip, but the wing doesn't pivot, just the tip pivots. And those are all certainly alternatives. And I don't think anybody knows what the right answer is at this point. That's all a bunch of trade studies.
Okay, sir. Thank you very much. Sir, the second question is regarding the selection of the cross section. So you pointed out in your earlier slides that during the study you have come up with a particular number, but what cross section do you select? Can you throw some light on that? How do you select the cross section?
Well, for the blimp, it's a circular cross section because the envelope is a traditional blimp type envelope. It's a pressure envelope, and so it's going to go to a shape that looks like this. The Ohio Airship is a rigid airship. It's a rigid frame with a skin over it. And it has gas bags inside. No, I take it back. It doesn't have gas bags. It has ballonets inside. The entire thing is a gas bag. And then it has ballonets to let air in the bottom. But it is a rigid airship. So that's the big difference between blimp and Ohio Airship, is that the blimp is basically a blimp that has plane aspects to it, as James aptly named it.
Okay, sir. Thank you very much, sir. Thank you for the presentation, sir.
Okay.
You're welcome.
Thanks. Thank you. Now we can move to Palniappan. He had a question and I wanted him to unmute and ask. Mr. Palniappan, would you be able to ask your question?
I have a very good wife. Look what she just brought me.
Lucky. You've been talking for a long time, so you deserve it. Okay.
Okay, another question?
Okay, I'll probably just read out his question.
Sure.
So his question is airplane wing design versus hybrid airship wing design. Is there any difference?
Oh, that is a really good question. And the answer is no and then yes. Initially, it's pretty much just design a good wing for the airplane, but when you get further into the details, you're going to want to adjust the geometry to take into account the flow field of the hull. And I don't know exactly what that's going to do. That's going to take, to really optimize it, that's going to take some really good, interesting computational fluid dynamics, because you're going to get a funny flow field around the wing, and that'll change the optimal shape. But that'll come later. But basically, in the beginning, it's it's plan form, it's aspect ratio, and that sort of thing. Yeah, that's a good question. Without a good answer yet.
Yeah. Okay. The next question is by Mr. Saurabh Bagare. Saurabh, please unmute.
Yeah, hi, Dr. Raymer. I think you must be exhausted since it's night in the US. But thanks a lot for your presentation. And like Mr. Sohan Suvarna, I am a research assistant of Professor Pant, and I am actually an alumnus of the university that is organizing this particular talk.
Okay.
So I have this small, not doubt, basically like an open-ended conversation with you about if you, like in these particular airships, you had a problem statement of an airship that has some kind of a lifting surface, correct?
You could say that, yeah. In both cases, the customer was interested in a hybrid airship.
Exactly,
right.
Exactly. So what was your motivation behind choosing a conventional envelope with wings and tail rather than going for a lifting body envelope itself, like a blended wing envelope or a delta wing envelope?
Well, the plimp was at least partly driven by the desire for the whole thing to fold up and be easy to transport. And that makes a configuration like this work quite well. In fact, one of the things I did for James, I don't think he minds me saying this, is that one of the designs that's actually fairly large will actually fold up and go into a standard shipping container. So it can be transported anywhere in the world easily. And you couldn't really do that if you had some kind of a big blended wing body or a delta wing or something like that. But another issue is that you don't want to add a lot of frontal area. And for something like this, well, I guess I don't know if you're talking about a blended wing body that includes the volume for the lifting helium. That's a whole different animal. But in any case, if it's like the plimp where the airship part is separate from the airplane part, then a blended wing body would just be adding a bunch of frontal area and drag. It probably wouldn't help much.
No, I meant an actual envelope in the shape of a flying wing that has the entire area is filled with the lifting gas.
You could do something like that. That's not the design I looked at, and that will have a lot more frontal area. So you have to watch out for that, or it'll. Well, I don't know. I guess you could do it without frontal area by having it a great big thin thing, almost like a triangular pancake. You can do something like that.
Yeah, such design generally came when I just Google Dynastat, so I see many random designs which are like triangular in shape and filled with the lifting gas.
Yeah, you could do that. It's going to have a lot of envelope surface area for the amount of volume contained. So you'll have some weight penalty and drag penalty because of that. But it'd be an interesting trade study. And when I get to design sort of an all-up kind of a system engineering approach, which takes a fair amount of money. But I like to do lots of trade studies and even trade studies in things that I personally think aren't likely to be the right answer, because I'm not always right. I always think I'm right, but I'm not always right. So yeah, I prefer to design 4, 5, 6 different vehicles for a given requirement and let the numbers sort them out rather than just trying to guess myself. So if I were doing such a big trade study, I'd probably do one design much like what you're describing, and then run out the numbers and see if it's better or not as good. It's not a bad thought. It's worth looking at.
All right. Thanks a lot.
Okay.
So friends, we have only 10 minutes remaining. So therefore, we don't want to really lose the opportunity. Shravan Kumar Bhadoria has raised the hand. Shravan, please go ahead quickly.
Okay, thanks a lot, Panji.
Yeah.
Hello, doctor.
Hello.
Yes, I'm Shravan from Shivnada University. Of course, like everyone mentioned, it was a great presentation, and that's true. I also felt the same. Sir, I mean, I'm more interested in knowing what kind of design software you have used to create this design. And this is my first question. And so second question is, as I'm currently seeing in this slide that the bottom portion is being attached to the what you call filled up envelope. I mean, I wish to know what kind of technology is used to attach these two parts together.
Okay, well, I'll do that one first. It's very standard airship stuff. Basically, on the inside, you have strings that run from the heavy items down below, and they go up to the hull. And then up at the hull, they're attached to what are called catenary curtains. Second time I said it wrong. Catenary curtains, and they're just bits of whatever the hull material is, and they're attached to the hull material, and they run usually nose to tail, and they transfer the loads. So that's basically what you have. So it's not empty inside. It looks like a spider went crazy on the inside and put all these strings all over the place. So that's basically how that works. As far as the software, I use my own RDS software, which I've developed over many years for aircraft design. And it's kind of a generic software. It's not tailored to any particular type of vehicle, so I can use it. And it has a CAD module, which I wrote, and also a lot of analysis modules based on the methods of my book. So that's what I use for my design. But then I take the geometry and I pass it out to other people on the team, people doing computational fluid dynamics, people doing structural design, mechanism design, and that sort of thing. So, and they put it into their own CAD systems and do whatever CAD system they like. So I give them an IGES file. Okay.
All right. Thanks a lot for the input.
Shravan, can I just add that this software is available through AIAA very easily.
All right. Okay.
Yeah. We have been given a copy by Raymer for our use for teaching. We purchased one official license, but yeah, moving on, there is a question from Ajay Vishwat. Ajay, please.
Hello, sir. Yes, sir.
Yes, hello.
Yes, sir. First of all, I'm so happy to be part of this presentation. So thanks for enlightening us for the same, on the Airship. I do have a question. Yes, sir. Nice meeting you, sir. I do have a question. We do have something called flight envelope for a fixed wing aircraft, right? The VN diagram, we call it. Velocity and load factor. So can you?
Yeah, sure. VN diagram is right. And then there's a flight envelope, which is a different thing.
Okay.
Yeah.
Sorry, sir. So VN diagram, we call it, right? So
Right.
how can you comment on the VN diagram of such hybrid airship?
Well, you just calculate it. It's no different than anything else. You set a maximum load factor, positive and negative, and that makes a line at the top and bottom. You set a structural maximum speed.
Yeah.
That becomes a structural design criteria. And then the only one you have to calculate is on the left. You have the two curve lines for stall. But you probably don't fly this thing upside down, so maybe you don't need the negative E part.
True.
But in the positive, that's where you have to do this tricky thing of having it only carry part of the weight, because the wing is only carrying part of the weight. So you have to take that into account in that left curve of the VN diagram. Otherwise, it's just like a normal airplane.
So it's going to be almost like the same that of aeroplane.
Yeah. So you calculate it the same way. You just take that one thing into account. When you do the stall line, take into account the hydrostatic lift.
Okay, sir. Thank you so much, sir.
You're welcome.
Okay, wonderful. So, are there any more questions? Because I don't have a question, but I have a request to Dan, which I will do in the last. So quickly, guys, if there are any questions, we can go ahead with that. And yeah. All right. So then, if there are no questions, I would like to make a request. So, as you might be knowing, I have sent an email. I think we are conducting a conference on LTA systems in June next year, and it will be the first such conference in India on LTA systems. And as part of that, we are going to conduct a few panel discussions. So one of them is going to be on conventional airship versus hybrid airship. And I thought that with today's presentation, you would be a very, very good person to maybe help us in conducting that panel discussion. We will invite 3 or 4 people apart from you, who would be champions of either conventional or hybrid or rotorcraft and all that. And then we would like you to help us out. So of course, we have to look at your convenience, your timing. But it would be real fun to have a debate and a discussion on conventional versus hybrid. Okay, so
it'd be an interesting panel discussion, and I'd have to look at my schedules and other commitments.
That's right. And also we have to look at the, we need to look at the timing.
Are you talking about in person? Because I would love to go to India again. It's been too long.
Yeah.
Last time I was there, your students allowed me to drive a tuk-tuk. That was very fun.
Yes. See, we are planning to conduct the conference in our institute in a hybrid mode. That is, we are going to have it, if the conditions permit, in the physical mode, as well as those who cannot come for some reason in the online mode. So it's a hybrid conference. But there is going to be an airship regatta on the last day. And in the airship regatta, we are going to have a competition approved by the Federation Aeronautical International. We're going to have a kind of an airship race in an indoor auditorium. So that is what is planned on the last day. And yeah, there are going to be invited talks. There are going to be contributed papers. So I'll send you an email with the link. In fact, Dr. Manish Tripathi is the technical chair of that conference. He will send you a mail with the details. And I think we'll be delighted to have you in we would love to have you in person, no doubt about it. But we understand that the situation is not clear right now. So we are
maybe ADA is ready for another aircraft design short course, and we could tie them together and get them to pay for my travel.
Right. We'll try to talk to them. We'll talk to ADA or to DRDO if we can conduct another course, and we could do that. Okay, so with that, I would like to pass on the control to Manikandan to formally close the session, and we are very lucky to be just in time.
Yes. First of all, I thank Dr. Raymer for accepting the invitation with your tight, busy schedule. And it was a very wonderful presentation and was very elaborative. And we have learned many things related to the hybrid airship, since it's a very hot research topic in the field of aeronautics. Thank you so much. Thank you so much for your valuable presentation. Thank you.
You're very welcome. Thank you so much. And all of you who listened, thank you. And thanks for those excellent questions. This was fun.
Thanks a lot. Okay.
To the participants, the next session will be in MS Teams. You can use the same link that you have used for the last 4 days. So we will meet at 11:30.
Bye, everybody, and thanks, Dan, once again.
Bye,
Thank you, sir. Thank you so much. Bye, sir.
Thank you. Bye-bye.